Interface mass transfer. Interface mass transfer is the mass transfer of solute from one fluid phase by convection and then through a second fluid phase also by convection. Equilibrium relations are important to determine the concentration profiles for predicting rates of mass transfer. One example of this transfer is the absorption of ammonia from air by water. Concentration profile in interface mass transfer. Majority of mass transfer system consists of two immiscible phases. An interface between these two exists. We can see from the diagram that on the right side of the interface is the gas phase, while liquid is on the left side. YAG and XAL is the mass fraction of solute in the gas and liquid phase respectively. YAI and XAI are the mass fraction on the interface. We can also see that NA, which is the mass flux, directs from higher to lower concentration. Now let's talk about mass transfer in equimolar counterdiffusion and diffusion through a stagnant fluid. In equimolar counterdiffusion, the rate of transfer of two species by molecular transport is always equal but in opposite direction. This can be expressed in the equation Ky times YAG minus YAI equals to Kx times XAI minus XAL. We can also see that the slope of the line can be equal to YAG minus YAI over XAL minus XAI. Same thing can be done with diffusion of solute A through a stagnant non-diffusing B. Diffusion through stationary gas occurs when one boundary of the diffusion system is permeable to only one component. You can see that same equation can be used, but the variable Ky and Kx have different values. You can see from these expressions that we can also define an equation for a slope of the PM line.
Hi, my name is Daiserdin Sotomayor and we will discuss on the overall mass transfer coefficients and driving forces. We will deal with the discussion on gas absorption in molecular level. To have an overview, we will include in these slides the introduction, the equimolar counterdiffusion and/or diffusion in dilute solutions, diffusion of A through stagnant or non-diffusing B. And lastly, we will discuss on the overall coefficients. To start with, we can define merely what a film mass transfer coefficient is. What is a film mass transfer coefficient? It is also known as the single-phase mass transfer coefficient, and according to Hincapoulis, it is often difficult to measure experimentally, in the exception that there are certain experiments designed so that the concentration difference across one phase is small and can be neglected. What is the overall mass transfer coefficient? It has the measurements based on the gas phase or liquid phase, depending on the side of interest, which is used for heat transfer and will be based on the inside and outside areas instead of the film coefficients. Here we shall see the two equations relating the mass flux and the mass transfer coefficients. Na equals K prime Y multiplied by the quantity YAG minus Y asterisk A is the equation for the gas phase in terms of the overall gas phase driving force. Here we can see that Na represents the mass flux, K prime Y is the overall gas phase driving force, YAG is the mass fraction of A in the gas phase, and Y asterisk A is the value of the mass fraction that would be in equilibrium with the mass fraction in the liquid phase. In this slide, we have substituted Y with X, and here we have Na represents also as the mass flux, K prime X is the overall liquid phase driving force, XAL represents the mass fraction of A in the liquid phase, and X asterisk A is the value wherein it would be in equilibrium with the mass fraction of A in the gas phase. So we have two equations. We shall discuss here the equimolar counter-diffusion and or diffusion in dilute solutions. Both are in the same concept where equimolar rates comes in and comes out through the interface. Here we can see the red box having the liquid part, the blue part, and the gas part in the purple one. So we can see inside the red box, the liquid is diffusing into the gas phase. This slide shows how the gas and the liquid interacts according in the diffusion. Let's say we have the gas here having a certain particular concentration diffusing into the liquid. That particular concentration, the liquid also will have to diffuse into the gas phase. So there is equimolar rates of counter diffusion. Equimolar means equal molarity, and then counter diffusion, diffusing in counterparts, meaning they are in counterflow. Here in the gas phase, we have the molar fraction of A in the gas phase and the molar fraction of A in the liquid phase. In the liquid phase, we have here the equal molarity of YAL and XAL, and in the interface we have YAI and XAI. Equimolar counter diffusion and or diffusion in dilute solutions have this equation. We can use Na equals K prime Y times the quantity YAG minus YAI, which are the mole fractions in the gas phase and mole fraction in the interface, having in terms of Kx or K prime X, we have the inner quantity as XAI minus XAL. The bottom equation shows that there is a mathematical property used to have this equation. Substituting that equation with the previous equation on the slide, we can have the slope of the line equal to YAI minus Y asterisk A over XAI minus XAL. And what's this for? This will be used to calculate for the resistance of the system based on the driving force of the phases. From the equation used with mathematical property, we will have YAG minus Y asterisk A equal to YAG minus YAI plus M prime XAI minus XAL, which is in the form of the linear equation Y equals MX plus B. Defining the YMX plus B equation in terms of K prime, we shall have this equation in the bottom. We can define the equation 1 over all the reciprocals of K prime Y and K prime X as the reciprocal of the K prime Y is the total resistance based on the overall gas phase driving force, while the small k prime Y's reciprocal is the gas film resistance. We can have the M prime over K prime X as the liquid film resistance, while we can define K prime X as the liquid phase mass transfer coefficient and K prime Y as the gas phase mass transfer coefficient. For the driving force base, we can have this equation all in terms of Y except for the equation or the term with the slope with K prime X, meaning 1 over K prime Y is equal to the quantity 1 over K prime Y plus the another term M prime over K prime X. Counter to the gas driving force base, we have the equation for the liquid driving force base as 1 over K prime X equal to the 1 M double prime K prime Y as the reciprocal of the K prime X, which is the liquid phase mass transfer coefficient. Having the trends, if the slope is quite small and there is a small YA or mass of A in the liquid phase, will give large amount of A in the gas phase, then the gas solute A is very soluble in liquid phase, having M prime over Kx prime X is very small. If that is so, 1 over K prime Y is equal to 1 over Ky prime, meaning the reciprocal of the overall mass transfer coefficient will be equal to the reciprocal of the overall gas mass transfer coefficient. K prime Y is the overall mass transfer coefficient, while the K prime Y small is the gas phase mass transfer coefficient. Thus, gas is controlling and the major resistance is in the gas phase, meaning gas solute A is easily escapes to gas phase or enter the liquid phase to dissolve quickly. And if the M double prime is quite large and gas solute is very insoluble in liquid phase, then the reciprocal of the M double prime K prime Y is very small, showing that the reciprocal of the overall mass transfer coefficient is equal to the reciprocal of the liquid phase mass transfer coefficient, giving the liquid phase is in controlling and the major resistance is in the liquid phase. Now let's go to the discussion of the diffusion of A through stagnant or non-diffusing B, meaning A or the solute A will only be the currently going into the liquid phase. Or let's say the solute A alone will be having its mass transfer. Shown in the illustration, only the solute in the gas phase will be going through the liquid part. As of the previous slides, we had the equations for the mass flux. Here we have the mass flux substituted with YAG minus YAI. In the substituted part is in terms of the interfacial part. Here we can see that we have substituted a term from the bottom equation to the first two equations in this presentation. And there is the difference that you can see given by the block with the red box. Because Ky is equal to K prime Y over Y minus AM in the interface, and Kx is equal to the K prime X over 1 minus XA in the interface, then we'll have the substituted values as the reciprocal of the overall liquid mass transfer coefficient and overall gas mass transfer coefficient in the previous slide in the form of Y equals mx plus b, where Y minus YA in the interface will be equal to the logarithmic mean of 1 minus Y asterisk A and 1 minus YAG. It will be similar for the mass transfer coefficient in the liquid phase, wherein the slopes that we will see is the M double prime and the M prime, wherein 1 minus XA in the interface is the logarithmic mean of the XAL and the X asterisk A. And now we will move to the discussion of overall coefficients. Note that the relations derived also hold for any two-phase systems where Y stands for one phase and X for the other phase. And this ends the discussion for the overall mass transfer coefficients and driving forces. The next slides will be for the design of plate absorption towers. Thank you.
I am Raymond Hernandez, and I will discuss the design of plate absorption tower and the derivation of its operating line. A plate or absorption tower has the same process flow diagram as the countercurrent multiple stage process. In the case of solute diffusing through a stagnant gas and then into a stagnant fluid, let's say the solute is acetone and the stagnant gas be air and stagnant fluid be water, the amount of air and water remain constant throughout the entire towers. Here is the formula to compute for the endpoints of the operating line. L prime times x sub naught over 1 minus x sub naught plus v prime times y sub n plus 1 over 1 minus y sub n plus 1 is equal to L prime times x sub n over 1 minus x sub n plus v prime times y sub 1 over 1 minus y sub 1, where v prime and L prime are the molar flow rates of air and water respectively. These values are constant throughout the entire tower. Thus, the formula will be x sub naught over 1 minus x sub naught plus y sub n plus 1 over 1 minus y sub n plus 1 is equal to x sub n over 1 minus x sub n plus y sub 1 over 1 minus y sub 1. To plot the points between the endpoints of the operating line, the formula is L prime times x sub naught over 1 minus x sub naught plus v prime times y sub n plus 1 over 1 minus y sub n plus 1 is equal to L prime times x sub n over 1 minus x sub n plus v prime times y sub 1 over 1 minus y sub 1, where x is the mole fraction of the solute in the liquid, y the mole fraction of the solute in the gas, L sub n the total moles of liquid, and v sub n plus 1 the total moles of gas. The number of theoretical trays are determined by simply stepping off the number of trays.